Imagine an AI that learns the physical rules of our world just by watching raw pixels. And it does it all on a single standard graphics card. Welcome to our podcast, Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik and narrated using AI-generated voices.
It honestly sounds like science fiction, but the reality of what we are looking at today fundamentally changes machine learning.
It really does. Welcome to today's deep dive. We're thrilled you are joining us today because our mission is to explore a genuinely groundbreaking new paper.
Yeah, it introduces this framework called LeWorldModel, or, LeWM for short.
Right. And the goal of this deep dive is to basically understand how we can teach an AI to actually predict the future. Like, how do we get it to build a world model in its head without the AI just getting completely overwhelmed by all that visual data?
Or even worse, taking these really lazy computational shortcuts.
Exactly. Because to appreciate the solution we're talking about today, we first have to look at the historical roadblock.
Yeah, typically when you ask an AI to predict what happens next in a video, the model tries to render every single future pixel.
And which is just a massive waste of resources.
Oh, completely. If a ball is rolling across a table, the AI is sitting there trying to calculate the exact lighting, the texture of the wood, the shadow of the ball, all of it.
It's trying to predict the exact color value of the background wall when, all that really matters is just the trajectory of the ball.
Right. It is incredibly computationally expensive.
And so to solve that overwhelming burden, the field developed this thing called Joint Embedding Predictive Architectures,
Or,
GPS.
right, GPVs.
And the best way to understand the philosophy behind a GPA is to think about how you, as a human, drive a car.
Oh, that's a great way to put it.
Like when you are merging onto a busy highway, you are not memorizing every single leaf on the trees blurring past your window, right?
No, of course not.
You aren't calculating the exact pattern of a crack in your windshield or, the precise shade of blue on a billboard.
If your brain tried to process all of that raw pixel data, so to speak,
Yeah,
you'd crash. Your reaction time would just be zero.
exactly. So instead, your brain creates this highly compressed, really compact, latent space. You throw away the noise and you focus only on the critical things.
Things like cars, the pedestrians on the shoulder, the road itself.
Right. And GPTs try to teach AI to do the exact same thing. The instruction is basically, don't predict the next frame pixel by pixel, just predict the next important state in that compact latent space.
But that conceptual simplicity hides a massive technical nightmare.
It really does.
Because as soon as you tell an AI it doesn't have to predict exact pixels anymore, you introduce this huge vulnerability. It's this catastrophic failure mode called representation collapse.
Yes, representation collapse.
I hear you.
We have to deeply understand this problem before we can even appreciate today's breakthrough.
It's the ultimate lazy shortcut.
It really is. Imagine you give the AI a test, right? You say, predict what happens next in this physics simulation.
And the AI starts churning the numbers and realizes that, well, physics is hard. Friction and momentum are complicated.
Right. But it also realizes it isn't being graded on drawing the pixels perfectly anymore. It's just being graded on whether its prediction matches the future state in its own abstract language.
So it cheats. It simply decides that every single current input and every single future input is exactly the same.
It just predicts a uniform gray box every single time.
Mathematically, it is a brilliant, terrible cheat.
Yeah, because if the AI encodes the current state as all zeros and predicts the future is also all zeros,
Then the mathematical difference between its prediction and reality is zero. The prediction error drops to zero.
the AI thinks it just got a perfect score. But in reality, it hasn't learned a single thing about the physical world.
Exactly. It's like a student realizing that if they just answer C on every single question of a multiple choice test, they might somehow trick the grading machine into passing them.
It's so frustrating. But before we get into the wild ways engineers have tried to fix this lazy behavior, we have a quick word to share. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
So, returning to this massive problem of representation collapse, what's fascinating here is how the field previously tried to force the AI to stop taking that lazy shortcut.
Right, because they tried a lot of things.
They really did. Let's examine two major approaches that kind of set the stage for LeWorldModel. First, you have models like DynoWM.
Okay.
Their solution to stop the AI from collapsing all its representations into a single point was to simply freeze a pre-trained encoder.
Wait, let me make sure I'm visualizing this correctly. So they basically take an AI vision system that was already trained on millions of images.
Yeah, like it already knows how to distinguish a dog from a car.
Right. And they just lock its internal weights. They say, you can't change how you see the world. You just have to use your old rules for this new environment.
Precisely. Because the encoder's parameters are completely frozen, it physically cannot collapse the data into that lazy gray box.
It's mathematically forced to output diverse representations based on its past training.
Exactly. But as you can guess, freezing the encoder bounds its knowledge to the past. It limits what it can learn.
So the only way forward is learning end-to-end, directly from the raw pixels of the new environment. But if you unfreeze the encoder, don't you just invite representation collapse right back in?
You do. And to combat that, researchers developed a second major approach, which we see in models like PLDM.
Oh, PLDM, right.
Yeah, to stop the collapse while still allowing end-to-end learning, PLDM uses a highly complex loss function. It uses 7 different mathematical terms to constantly monitor and punish the AI if it tries to get lazy.
Okay, let's unpack this. 7 different mathematical terms.
Yes, 7.
The source material mentions things like variance, covariance, and temporal similarities. So if I'm understanding this, variance is trying to force the data points apart so they don't clump up.
Right.
And covariance is trying to stop the AI from just repeating the same feature over and over. I mean, that sounds like spinning cleats on a tightrope. Isn't balancing 7 different competing penalties incredibly unstable?
It is notoriously unstable. To make a model like PLDM work, the researchers have to manually tune 6 different hyperparameters.
6, wow.
Yeah, think of them as these highly sensitive dials. If you adjust the weight of the variance penalty just slightly too high, the model overcompensates and basically shatters the latent space.
And if you dial the covariance penalty slightly wrong,
the whole model might fail to learn entirely. It requires massive amounts of trial and error, it scales very poorly, and it's phenomenally computationally expensive just to stop the model from crashing.
So if freezing the brain is too rigid and juggling 7 math equations is too unstable, there had to be a middle ground.
There had to be. The field desperately needed a simpler, more elegant solution to train world models from raw pixels.
Right, without freezing the vision system and without requiring a PhD in hyperparameter tuning,
Yes.
just to keep the thing alive.
Exactly.
And that is exactly the void that LeWorldModel, or LeWM, fills. It solves this massive stability problem using only 2 loss terms.
2 terms. The reduction in complexity is staggering. Moving from a precarious 7-term loss function to a highly stable 2-term function is a structural triumph.
Let's look at those 2 terms, because the first one is just a next embedding prediction loss, right? The paper notes it uses teacher forcing.
Yeah, teacher forcing.
Which, for anyone not steeped in machine learning, teacher forcing is basically like having an answer key right next to you while you take the test.
That's a perfect way to describe it.
During training, the AI predicts the next state, and it's immediately penalized based on the actual true next state provided by the teacher. It keeps the AI grounded in reality.
Right, that's standard stuff. But the second term is where the real magic happens. It's a regularizer they call segreg.
Segreg. Okay, what does that stand for?
Sliced isotropic Gaussian regularization.
Yeah, I'm going to need you to break that down. Can you explain segreg in plain English?
Yeah.
How exactly does this one specific term stop the AI from taking that lazy collapse shortcut?
Let's break down the mechanics. Segreg enforces Gaussian distributed latent embeddings.
Okay, so a Gaussian distribution is basically a bell curve.
Yes, but we are working in high-dimensional AI space. So by projecting the AI's internal representations onto multiple random directions and applying a strict normality test, it forces the data to spread out evenly.
So it guarantees diversity in the latent space.
Exactly. It constantly audits the AI to make sure its data points are spread out smoothly across the multidimensional space.
So what happens when the AI tries to cheat? Like if it tries to collapse all the data into a single point just to get that 0 error prediction?
The moment it tries to clump the data, it fails that normality test. The loss function immediately spikes, and it forces the AI to push those data points outward again. It physically cannot collapse its answers into a single point. It must maintain diversity.
That is such a brilliant mechanism. Instead of juggling 7 different rules, segreg just enforces this one overarching geometric rule, spread out evenly.
Yes.
And the most crucial detail here, the real aha moment, is what this does to the tuning process. Because it handles diversity so cleanly, it reduces the tunable loss hyperparameters from 6 down to just 1.
A single hyperparameter, lambda.
This is one dial.
And they typically just set it to 0.1 across all these various tasks. It's incredibly stable.
Going from tweaking 6 highly sensitive dials and praying it doesn't crash,
Yeah.
to just setting one dial and letting it run, that is huge.
It really is. And we need to emphasize why this accessibility matters to you, the listener. Because of this streamlined math, LeWM only requires 15 million parameters.
15 million, that is tiny.
Astonishingly compact. It trains end-to-end directly from raw pixels on a single GPU in just a few hours.
A single standard graphics card. You don't need a massive corporate server farm to run this. It completely democratizes AI research.
It puts state-of-the-art world modeling onto hardware that normal developers can actually access.
Here's where it gets really interesting, though. Because you might logically assume that by making the model so lightweight and so mathematically simple, they'd have to sacrifice performance.
You'd think it would just be a toy model.
Right. But when you look at the real-world performance, it is blazing fast.
Oh, the planning speed is where LeWM truly separates itself. When an AI controls a robot, it has to simulate multiple possible futures in its head to decide the best action to take.
Let's look at the hard numbers. Compared to DanoWM, the model with the frozen brain, LeWM achieves a 48 times faster planning time.
48 times faster.
It completes a full planning cycle in under 1 second, 0.98 seconds. DanoWM took 47 seconds to plan the exact same actions.
Yeah, if you have a robot operating in the real world, 47 seconds of lag between seeing an object and deciding how to grab it is useless. Under 1 second is real-time interaction.
And it significantly outperforms both PLDM and DanoWM on complex tasks. Like, look at the push-T task.
Right, push-T.
Where a robotic arm has to use friction and momentum to push a block into a specific zone. LeWM achieved a 90% success rate on this task under a fixed compute budget.
While DanoWM only managed a 13% success rate under those exact same limits.
90% versus 13%. And it does this on another task, OG Bench Cube, despite using 200 times fewer tokens.
200 times fewer tokens, yeah.
To me, it's like comparing a master chess player to a novice.
I like that.
The novice is staring at the board, completely overwhelmed, overthinking every single piece. But the master instantly sees the entire board as a perfectly organized state. They can see 10 moves ahead instantly because their mental representation is totally stripped of noise.
That's a highly accurate analogy. The master has a superior physical intuition. And through linear probing, the researchers actually proved LeWM's latent space encodes real physical structures.
Just purely from watching pixels.
Purely from watching pixels. It learns the actual agent pose and block pose without ever being programmed with a physics engine.
That leads right into one of my absolute favorite parts of the evaluation, the violation of expectation test.
The surprise test, yes.
They wanted to see if the AI could actually get surprised. Because if you aren't surprised when a block suddenly teleports, you don't actually understand physics.
Right. So they altered the simulation to make a block spontaneously teleport across the screen.
And LeWM's prediction error sharply spiked. It literally got surprised by a physically implausible event.
It knew solid blocks don't just teleport. And then there's this beautiful emergent property they found called temporal straightening.
Temporal straightening? That sounds wild. What is that?
As LeWM trains, the paths in its latent space naturally become straight and smooth over time. An untrained model might take chaotic, zigzagging routes to predict the future. LeWM naturally carves a straight, highly efficient path.
And what's crazy is PLDM had a specific math equation dedicated entirely to forcing those paths to be smooth. But LeWM doesn't.
Right. There is no explicit rule in those two simple lost terms telling it to do so. It is an entirely emergent property.
Just because the SIGREG term is so clean. But, we have to look at the whole picture here. The model isn't completely flawless.
No, it has an interesting limitation.
Yeah, in the absolute simplest environment they tested, this 2D navigation task called Two Room, LeWM actually struggled.
It did. And if we connect this to the bigger picture, it all comes back to that core innovation.
Right.
The SIGREG term and the Gaussian distribution.
Right, because SIGREG rigorously demands that the data spread out and fill this high-dimensional space.
Exactly. But the two-room environment had such low complexity that it just couldn't fill out the high-dimensional Gaussian prior.
So, ironically, the model is so advanced and primed for complex physics that it hungers for rich data. It fails when things are too simple.
It gets confused by its own excess capacity.
So what does this all mean? Why does this matter to you as you listen today?
It's a huge shift.
It really is. This deep dive proves we are moving toward adaptable, real-time robots that understand the physics of their environments intuitively.
Without needing perfectly engineered million-dollar data centers.
Exactly. We are looking at the foundation for robots that can instantly compress visual data and plan physical actions in real time, all on standard hardware.
And it leaves us with a truly fascinating final thought to ponder. If a model like LeWM can build such a robust physical intuition purely from visual observation, just from watching pixels, where does it end?
Right. What's the limit?
Could future iterations learn to see invisible physical forces like wind or temperature gradients or even human intent just by observing the subtle secondary effects they have on the visible world?
That is an incredible thought. Learning the invisible by mastering the visible. Thank you for listening to our podcast. If you enjoyed this episode, please subscribe and leave a review. We appreciate your support.